So week 5 is about modeling and analysis techniques of switched mode power converters. So we may not be solving more problems like the other weeks, but the objective is to learn the detailed process. So that's why I have not considered many problems this session, but we'll be understanding the concept behind it, how we are going to get the equivalent circuit model, or how do we do the state space averaging or the circuit averaging method. So I'll be covering both the methods, but I'll cover in detail. So we may not be able to solve more problems, but whatever we'll solve properly, so that you will be able to solve other problems. So understanding the concept is critical for today's class. So it's not about solving many, but it's not about the quantity, it's about the quality. Yeah. So the first problem is consider the following switching network and obtain its equivalent circuit model. So here I have considered one switching network, half bridge switching network, and it is similar to that of what you see in a buck converter. Now we are asking the equivalent circuit model. So we need the relation between V1, I1, V2, I2, and we need to do the circuit averaging technique. So we have to apply circuit averaging, whatever sir has discussed. But again, I will show how to do it in detail. So before we start, can anyone give any idea or how to solve this problem?
Do we start with writing KVL equations?
Yes, very good. Then
We have to solve it for state variables.
yes, yeah, you're sort of right. So let us assume that the duty ratio for this is Q. So for this it will be Q bar. So now can you tell me the relation between I2, I1 as well as V2 and V1? So what is I2 when switch is on? So let us start from the basic. So what is the value of I2 when Q is 1 and when Q is 0? I2 is equals to I1. So when Q equal to 1 and Q equals to 0. Okay, so someone said when Q equals to 1, I2 is equals to I1. So what about when Q is equals to 0?
I2 equal to 0.
0, right? Yeah, good. So similarly, let us do for voltage also. So what is voltage when Q is equals to 1 and when Q is equals to 0?
Drop across the switch will be there.
Ideal
V2
switch.
will be
Assume
V1
ideal switch.
minus
Ideal switch. So no
V2
drop.
it is V2 equal to V1.
Yes, very good. And thanks for pointing it out. So it's an ideal switch. Yes. So VT equals to V1, right?
Yes.
And 0. Is this correct, or is there any mistake?
Yes, it's correct.
It's correct. Okay. So now in circuit averaging or in any state space averaging technique, first we have to write everything in terms of Q. Then we'll write in terms of duty ratio, or we can directly write in terms of duty ratio. So say Q equals to 1 has say dt time, and then we'll have to perform averaging on top of that, and say this is having 1 minus d into t, and then this is having also dt, and this is also having 1 minus d into t. So now tell me the expression for I2 and tell me the expression for V2 in terms of d as well as I1. What is average value of I2 over a cycle t? So for dt time it is I1, and 1 minus dt time it is 0.
is
So
0.
what will be
So it will be I1 into D2.
E? Yes, very good. So it will be I1 into D. Similarly, V2,
V1 into D.
V1 into D. Very good. So this is the average of I2 as well as V2 over a cycle of T, where T is the time period. So here T is the time period. Okay. So what do we do in circuit averaging as well as state space averaging? So what we consider is, we consider an average value. So it will have a DC value. So first of all, we'll neglect the ripple. Upon neglecting the ripple, we'll consider the average value, and on top of average value, we'll excite it with a small perturbation. So that perturbation, we represent it using tilde, which will eventually be used to get the small signal transfer functions, and then the DC value that we are considering will let us know the DC analysis. So the circuit will have two things: one is DC value, one is the small signal AC value. So using DC, we can perform DC analysis to find the operating point. Using the small signal perturbation variable, we can get the small signal transfer function or the small signal model, which we can use for designing the controller in the upcoming weeks. So basically what we do is, this average is there, right? I2 of T. We'll consider its actual average value plus some AC excitation for all the variables. Similarly, if you consider V2 over an average, we'll consider V2 plus V2 tilde. Similarly, we have I1 average is I1 plus I1 tilde. Similarly, V1 is equals to V1 plus V1 tilde. Similarly, we have to consider for duty ratio, we'll consider D steady state plus D tilde. So now what we are considering, all the values that we have done, whatever we have averaged out over a cycle, we are representing using one DC value, which are represented by the capital values, plus some AC excitation. So we are perturbing the value. Kindly note that this perturbation is not ripple. We are totally neglecting ripple. So then, since this is, we are eventually doing the small signal model, what we are doing is, we are averaging out all the variables over a cycle. So the ripple information is lost. And after that, we are exciting with a small signal variable or small signal excitation, which is this tilde. So one is the DC value at the operating point, and the other one is the small signal excitation. So now we have to substitute this in this given expression to get whatever we are desiring to get. So far, is it
Excuse me,
clear?
sir.
Yes, yes.
Sir, actually, can you please differentiate this two terms, circuit averaging and state space averaging?
Okay, okay. So both are actually giving us overall, the final objective is to get the either the DC value or the small signal model. So let me start explaining it a little bit briefly. So circuit averaging. So the overall final objective is to get the DC operating point. So we have to get a DC equivalent model, DC model, as well as an AC model. So this will be used to get or solve for the operating point. And then this will be used to solve for the small signal transfer functions. So both are the final objectives in either of these methods. So both the methods will make you reach the same destination, but they are two different paths. And this is the destination. So solve for small signal transfer functions. So this is like the destination, whatever we are wanting to achieve. This is the destination. Now, what does circuit averaging do? What does state space averaging do? So in both these methods, we are considering small signal excitation for each of the variables, right? So whatever voltage, current, duty ratio, we are considering one average value plus one excitation. So any data variable x, we are considering x steady state plus x tilde. So x averaged over a cycle t. So this is my DC value at steady state, and this is the small signal AC perturbation or AC excitation. Okay. So in the case of circuit averaging, so if I consider circuit averaging, what is the process? So in the case of circuit averaging, as you mentioned, we'll first write the KCL, KVL, and then apply this steady state x, replace x by x steady state plus x tilde, and then we'll solve for it. Okay, and we'll solve again, we'll show, and then finally we'll try to represent in terms of a circuital representation. So we'll represent in terms of a circuit. So we can actually get the feeling of how the inductor is changing, how the capacitor is changing. So basically we are representing it in terms of the circuit itself. Whereas in the case of state space averaging, so instead of KVL, KCL, we'll start from the state space model. State space model, and then on top of that we'll again do the same, whatever x we have will average, but here it is in terms of state space, right? Because everything is in terms of matrix. So finally you will get in terms of matrix representation. In the first case, we are trying to represent in terms of circuit, so we can get a feeling how or what is affecting our pole, what is affecting our zero. So if you if you implement everything in terms of circuit, you can actually see what is going on and everything. But as the number of variable increases, say in a buck converter or boost converter, we have two variables, right? State variables like IL and VC. So it doesn't matter whether you're doing circuital way or matrix way. But say if I have 7 states, then writing 7 equations and then combining and then doing it manually will be difficult. In that case, if we write everything in terms of matrix A, B, C, D, I can solve everything in terms of A, B, C, D. And then finally, I'll get everything in terms of matrix. So if I am solving for any steady state point or small signal transfer function, I can use MATLAB and then plug in the matrices and then perform the matrix SA minus A inverse into B, C into SA minus A inverse into B. So it will reduce my burden of solving it manually. But what are we missing in the state space averaging? So we are, in the case of state space averaging, we are just writing everything or representing everything in terms of matrix. So we will not get the final mathematical expression. So we will not see which parameter is affecting the zero, which parameter is affecting the pole, which we can get using circuital. So if you have circuit, then we can see by changing this parameter, by altering this parameter, this will get changed. So you'll get that physical insight, or you can actually get the feeling of what is going on using the first method, where you will draw the circuit itself. Whereas in the case of second one, you can do this when the system is getting complicated. So both the methods are just two different paths to reach the same destination, and each have their pros and cons, but it is advised to learn both of them. But in this case, in this course, sir has emphasized more on circuit averaging, because all the transfer functions, that everything has derived from the circuit itself, and everything will be in terms of parameter RC, R and C. So you will get the expression for poles and zeros, and now you can see that by increasing the capacitance, how the pole is moving or how the zero is moving. So you'll get these insights from the circuital representation. which is basically the circuit average. In the case of state space averaging, everything you will be getting in terms of matrices. So for a buck converter or a boost converter or a buck boost converter, it is C into S minus A inverse into B. The matrix will change, but you cannot get anything out of it, right? Like you will not know by changing what exactly will change. But as the system's complexity increases, hello, 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 can you hear me? Hello, 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 anyone?
Yeah, now it is audible, sir.
Okay, actually, there is
2
a
minutes
power.
back.
Hello. Actually, there is a power cut here. Just let me know whether you are able to hear me. Or
Yeah, you are able to hear, sir.
okay. Actually, there is no power, but luckily Wi-Fi is still there, so I think we can continue. So these are the pros and cons of these two methods. So far, if you have any queries, you can ask.
We're having one more term called as a large.
Sorry, can you please
Hello.
repeat? Yeah.
Actually, we are having one more term called, right, large signal modeling.
Okay, large signal model and small signal model. What are those two?
Yes, sir. So you
Yeah.
are writing this X average as X steady
Yes.
state plus X field day, right?
Yes.
If you are not adding this AC perturbation, then it is called as large signal modeling, correct?
Yes.
Whether am I correct?
Yes. In some sense, but I'll explain. You tell me what you are thinking, so I can correct, and then I'll try to explain.
Okay.
So as you said, this tilde will not come in large signal model, which is to some extent is correct. Why? Because in the case of large signal model, sorry, yeah. So if you see this for example, let us consider a buck converter itself, right? In a buck converter, we have this switching configuration, and you know that any switching is non-linear behavior because there is a discontinuity, right? Q is changing from 1 and 0, so it is not a linear system. It's a non-linear system because of the switching. So if I write I2 in terms of this Q, then that's the actual original model where I am not making any assumptions. So no assumptions are there. So if I am considering that model, that is called large signal model because it has the switching action as well as the ripple behavior in the model, and we are not making any assumptions. Now for our simplicity, say if we are planning to design a controller, I need a small signal model. And the question is, why do I need small signal model? Because we have learned designing the controller using transfer function based approach, S domain based approach. So for the given nonlinear system, I need a transfer function. And we have also learned that transfer function is Laplace transform of a LTI system, right? But the system is nonlinear. So what we are trying to do using these methods, that whatever two methods, we are trying to linearize the given nonlinear system. So how are we linearizing it? We are considering an average. So first thing what we are doing is we are averaging out all the variables. So the ripple information is lost. Now we are considering only the DC value, and then on top of that we are exciting it. So we are trying to linearize the switching action, which was the original nonlinear part. And once we are linearizing it, we have the DC value, and we are also exciting it with some small signal AC perturbation. So finally, we will be getting one DC model, which we can use for solving the operating point, and the other one is the AC model, which we can use to solve for the small signal or obtain the small signal transfer function. So the original actual model without any assumptions is called large signal model. The linearized model, where we have made an approximation or we have neglected the ripple and obtained the final AC model, is called small signal model. So what are we missing in the small signal model? We are missing the ripple information. So we have neglected something. So how is it going to be reflected, or what are the consequences by neglecting this ripple information? Since we have neglected something, the consequence that I think sir will be explaining in the upcoming weeks, but I'm giving you the information ahead. So the model will have validity issues because we are neglecting something. It is not valid throughout the bandwidth. So how is it limited? So using this small signal model, you will be able to design the controllers up to a bandwidth of 1/10 of the switching frequency. So I cannot use this small signal model to reach or to achieve transient response or performance beyond certain bandwidth. What if I want to achieve better than that? Then I can't use small signal model. I have to use large signal model where there is no ripple approximation. So where we consider the full ripple information, where we consider the switching. So that is large signal model based approach. Whatever we are learning now is small signal based approach. So if you ask me, sir, why do I need to do small signal? Why can't I directly do large signal without making assumptions? It is difficult.
Yeah, that is
Also,
the question arising in my mind.
yeah. So exactly. Why to learn two things? So again, large signal using large signal model, things may get complicated, and of course it will get complicated, which you will see in the upcoming weeks, because it is not easy to understand, also not easy to design, because you have to consider the switching behavior. And in the basic converter that we have only one switch, Q equals to 1 and Q equals to 0. Say in non-inverting buck boost, we have 4 switches, and in some other converter, we have more number of switches. Then it is not easy to consider the switching configuration and consider the large signal model, which will be little bit difficult for someone who is learning the controller design. So it is equally important to learn small signal, because small signal, although it has model validity, it is simpler to understand. Everything will be converted to S domain. You can use any toolbox in the MATLAB, or you can do pole zero cancellation by yourself to design the controller, which was our overall main objective. But since it has model validity, since the model is not valid beyond certain bandwidth, we also have to learn large signal. So one is to achieve better response using large signal. One is to simplify things. Say if my bandwidth 1/10 is okay for certain application, then why to trouble myself using a large signal model and complicating things when I can go for small signal model and design in a simpler way. So that's why it is important to learn both, and depending upon the application, depending upon the difficulty, which one to choose, that again is the designer's choice. Whether my application demands 1/20th of the switching frequency, why to trouble myself? I'll go with the small signal model and then design, and the application or the customer requirement is met. So that's the overall aim, right? So that's why we are learning both. So for a beginner, it would be difficult to learn large signal model. So that's why the course structure is also made in such a way. First small signal is covered, then you will understand large signal.
Yeah, thank you. Nice
Yeah,
explanation.
yeah, thank you. And in small signal, again, we have multiple methods. So we always have to learn both the methods. Like one such example that I think I had given in my previous course was sorry, like two methods are there, right? Like one is using KVL and another using KCL. So you can solve any circuit by just doing KVL or just by doing KCL. One is nodal analysis, one is loop analysis. So my personal preference is I'm comfortable with nodal analysis, but there will be circuits where loop analysis will be just a single step and nodal analysis will take three equations, and vice versa. Like in some problems, this may be easy, that may be difficult. So it is always good to learn both. So depending upon the given circumstance or given application, I can make my life easier by choosing one of the approaches. So here also the same. Is that clear?
Yes, yes.
Okay. And actually, there is a power cut. Luckily, Wi-Fi is still working. There might be some network issues, and I think my laptop might also run out of charge. So if you face any issues, just unmute yourself and let me know. Else, I'll be teaching to no one. So just be interactive so that I'll also know that I'm online at least. So that's why I have turned off my video also. Okay.
Okay.
Yeah. So moving on to our problem. So what we are trying to do is we will try to update these terms and then draw the circuit representation of them. So Yes. Okay. So we will do the same what we have discussed just now. So it will be I2 plus I2 tilde is equals to I1 plus I1 tilde into duty ratio is D plus D tilde. So let us multiply and simplify. So I2 plus I2 tilde is equals to D into I1 plus D into I1 tilde plus I1 into D tilde plus I1 tilde into D tilde. So tilde is a small terms, very small perturbation. If I'm multiplying two small terms, it will be much smaller. So this is another approximation that we do. We consider the second order terms or higher order terms to be 0. So as you see, we are making multiple approximations. So we are making multiple assumptions. So there will be a consequence. The consequence is bandwidth limitation, but we are doing this for our simplicity, just so we can get a linear model. Again, I1 tilde into D tilde is like a product of two variables. It is non-linear. So the final aim is to linearize the model. So whatever gets me to a linearized model, I'm assuming or making assumptions. So we are getting the benefit of small signal model at the consequence of limited model validity. So this is I2 plus I2 tilde is equals to, what I'll do is I'll segregate D into I1 plus I1 tilde plus I1 into D tilde. So we'll see why we have segregated and what is the advantage. So this is one equation that I have obtained. Similarly, I'll get for voltage. Let us see. I'll use the same color so we can correlate. V2 plus V2 tilde is equals to V1 plus V1 tilde into D plus D tilde. We have V2 plus V2 tilde is equals to V1 into D plus V1 into D tilde plus V1 tilde into D plus V1 tilde D tilde. Again the same second higher order terms I'm neglecting. So let me write what I'll be getting. So I'll be getting V2 plus V2 tilde is equals to D into V1 plus V1 tilde plus D into V1 into D tilde. So why we are segregating, that you will know shortly. So in a transformer, you know that if the turns ratio is N1 is to N2, you will get this relation V1 by V2 equals to N1 by N2 and N1 I1 equals to N2 I2. So here it is something similar. So that's what we are going to do now. Yes. So what we will be doing is the same thing. Here we have V1 and I1 on one side and V2 and I2 are on the other side. So I'm there, right? I'm online. I hope I'm in the call. Can anyone please confirm?
Sir?
Yes, sir. Yes, sir.
Yes. 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 Okay. And I think I have made one mistake. It's actually the other way around. I1 is equals to I2 because this is the load, right? So I1 is equals to, we should write I1 equals to I2 because in a buck converter I1 is equals to D into I2, right? So we have made a small mistake over here. Let me correct. This is I1. I1 should be in terms of I2. So this is I1. This is I2 because the load is always being connected. So I2 is not in our hands. The supply is in our hands. So whether the supply will supply the current or it will not supply the current. So whether I1 will be equals to I2 or I1 is equals to 0 because I2 is what the load is demanding, right? So similar to buck converter. So we have made this mistake. So let me modify this I1 and this is I2. So in the end, I1 will become 2, 2 will become 1.
So there I2 also will be 0, na sir, if Q bar equal to 0.
No. Actually, see, say I have a resistor over here. Then
Okay.
I2, yeah. So not actual resistor. Say I have a capacitor I can connect an inductor like a buck converter. If you see
Okay.
here, I can connect an inductor, and then after that I can connect a resistor. So this current is always flowing, but the input current will be 0, right?
Okay. Okay. Okay.
Yeah, like a buck converter. Yeah, sir. So yeah, that's
Okay.
what I got also confused, but I found that mistake. So sorry about that. I'll just quickly replace this. So this is I1 equal to I2 into D. I1, I1, I2, I2. Yeah, this I have realized based on the voltage and current relation. So how we can represent this? So we can see that there is a transformer based relation. So what we will be doing is we will draw a transformer. So voltages are the same. So here I have plus minus V1 plus V1 tilde. This is plus minus V2 plus V2 tilde. So V2 is D times V1 plus V1 tilde, right? So this is the dot convention and the ratio is 1 is to D because V2 is,
Transformation ratio will be.
yes, yes. So it is D into V1 plus V1 tilde plus some other term. So that term will be coming in between. So I'll use a different, yeah, minus and plus, and this is V1 into D tilde. So this voltage will be plus minus D into V1 plus V1 tilde, but V2 plus V2 tilde is this voltage plus a certain voltage. So that's why we have this dependent source because it is dependent on the D tilde. Similarly, if you come on the LHS side, so first let me draw the current. So if this current is I2 plus I2 tilde, then this current will be D into I2 plus I2 tilde. But my input current is I1 plus I1 tilde, which is this current plus some other current. So again, there will be a dependent source over here, which is I2 into D tilde. So now what happened? We have obtained the two equations, one for voltage and one for current, and now we have tried to represent in terms of circuit. And I can understand, like if you are learning for the first time, you can ask, sir, how do I know how to represent this? So in the beginning, when you are learning, it will be difficult, but once you do it for 2 to 3 converters, then you will understand, and then you can do for complicated circuit also. So the overall objective is to write everything in terms of transformer. So again, this transformer turns ratio is 1 is to D. For this, in the boost converter, it may be something else, 1 minus D dependent. So this you will learn once you write the equations, which one to segregate, because I need voltage V2 plus some voltage is equals to turns ratio into some other voltage. So once you do that, you have to segregate currents also, and the other terms will be dependent current source or dependent voltage source. So once you learn, then this will be there at the back of your mind whenever you're doing for some other converter, that you have to segregate and represent in terms of circuit. So from the circuit, now you can see that this voltage is dependent on this duty ratio D, this voltage V1, as well as the steady state voltage V and D perturb. So now you can correlate what is actually affecting what. So you can get that physical insight, and then you can imagine based on the circuit what is exactly happening. So in this way, you can get this insight once you represent or write everything in terms of or draw in terms of circuit. You can see what is actually happening. Else it feels like as if you are a bit blind because you are not following what is happening, where this happens in the second method, which is state space averaging, which we'll see now. So far, is it clear?
Yes, sir.
Okay. Let's hope we'll be able to finish this other problem also. So coming to our second problem, consider the circuit shown below, identify the circuit, perform the small signal modeling and write its small signal state space model. So can anyone identify what is this converter?
It's a combination of two converters.
Yes, which very good. Which converters are those?
I think
Buck boost.
Yes, very good. So they are buck as well as boost. So that's why it is called non-inverting buck boost converter, because the output is not inverting buck boost, but it is non-inverting. So that's why it is non-inverting buck boost. So very
so
good.
it is
So
a
this,
synchronous.
yes, synchronous as well. So this is the buck part, and this is the boost part. So it is a combination of buck as well as boost. So now previously we have done only for switch. Now we'll be doing for switches as well as this inductor. But since they have asked the small signal model, small signal state space model, we'll only be bothering about inductor as well as capacitor. So we'll see how to do this, and we'll get overall small signal state space model. So the time is less than a minute. The meeting might end. So if the meeting ends, kindly come back, and the power is also back. So there is no issue. We can continue. So what is VL? And what is IC in terms of when Q is equals to 1 and when Q is equals to 0. Here also when Q equal to 1, Q equals to 0. In terms of V in and VC. Buck boost. So question please. So someone is asking to repeat the question. Consider the circuit shown below. Identify the circuit, perform the small signal modeling, and write its small signal state space model. I think the meeting might end. Come back quickly. So when Q is equals to 1, this switch will be on and this switch will be on. So VL is nothing but V in. And when Q is equals to 0, this switch will be on and this switch will be on. So VL will be minus V0. Similarly, IC, when switch S is on, output will be disconnected. So it will be minus I0. For when switch is on, it will be IL minus I0. Clear? Is this equations clear for everyone? If you have any doubts, please ask. Simple, right? Okay. No questions,
Okay.
right?
Yes, sir.
We can
Okay.
proceed.
Yeah. So now I'll do the same thing. So first what I'll do is I'll write VL is equals to Q into V in minus Q bar into V0. Then I'll represent it in terms of duty ratio. So VL is equals to D into V in minus 1 minus D into V0. So now I'll replace everything by its average value plus perturbation. So I'll have VL plus VL tilde is equals to D plus D tilde into V in plus V in tilde. So I'll use the entire space. So let me make it closer. Yeah. Minus, again D will be D plus D tilde. So 1 minus D minus D tilde into V0 plus V0 tilde. So I'll get VL plus VL tilde is equals to D into VN plus D into Vn tilde plus D tilde into Vn minus 1 minus D into V0 minus 1 minus D into V0 tilde minus minus plus D tilde into V0 minus minus plus D tilde into V0 tilde. So first thing I'll do, whichever are did we miss something? I think here there is one term that I have missed, which is d tilde into v in tilde. So since this is second order, first this I'm considering 0, the approximation that we are doing. And if you see the DC values in a non-inverting buck boost, V naught is d by 1 minus d into Vn, right? So if you substitute that, this DC value will also get cancelled. And you know that average value of inductor at steady state is, voltage is 0. So this will be also 0. So this will be 0. The other two will get cancelled out. So now let us write the overall expression. So VL tilde is equals to d into V in tilde plus d tilde into V in minus 1 minus d into V naught tilde plus d tilde into V naught. Is it clear so far? Any confusion?
No,
Or
sir,
should,
we can.
okay. So this is my equation 1. So what I have done is, I have first neglected the second order terms because it is non-linear and it is also small, the assumption that we have talked about. Then I have also cancelled out the DC values. So if you see, if I want to get the DC operating point, then from here also I can get dVn is equals to 1 minus d into V0 and V0 equal to d by 1 minus d into Vn. So as we have discussed, it will have two things. One is the DC value as well as the small signal. So I can segregate the DC to get DC model and segregate the AC to get AC model. So even without knowing, I can cancel out all the DC values to get the AC model. Similarly, I can cancel out all the AC model, AC terms to get the DC. So it has basically two things. One is DC, one is AC. So I can segregate both. And it is true. It's not that I'm making any mistake. So now coming to IC. IC is equals to Q into minus I naught plus IL minus I naught into 1 minus P. So we are doing the same for IC. So IC is equals to Q into minus I naught plus 1 minus Q into or Q bar into IL minus I naught. So if you simplify it, you will get 1 minus Q into IL minus I naught. I want everything in terms of IL as well as V naught. So 1 minus Q into IL minus V naught by R. So now let us do the same thing. We'll substitute. So I'll get IC plus IC tilde is equals to 1 minus D. So Q will be D and D is D plus D tilde. So D minus D tilde into IL plus IL tilde minus V0 plus V0 tilde by R. So I have IC plus IC tilde equal to 1 minus D into IL plus 1 minus D into IL tilde minus D tilde into IL minus V naught by R minus V naught tilde by R and plus minus D tilde into IL tilde. So first thing, the second order term will neglect it to 0 and then all the DC values I can remove it because we are only discussing about the AC model. So I have first neglected the second order terms, higher second order terms, and then DC values also I have segregated. Now if you draw, I'll get IC tilde is equals to 1 minus D into IL tilde minus D tilde into IL minus V naught tilde by R. So this is my other equation. Is this also clear? I think I have gone a little bit faster for the math, but again, you have to solve. Whatever you are solving, you try to solve by yourself and then see. Maybe I am making mistake and you are not pointing it out, but the method or the concept should be clear. So what we are doing is simple. We are writing the equation and then we are averaging it out and then we are replacing the terms and then we are removing the higher order terms as well as the DC values to get these expressions. So now I have to write this in terms of state space. So what I will do, I know that VL tilde is equals to L into DIL tilde by dt and then IC tilde is nothing but C into DIC tilde by dt. So far clear, or do you have any doubts? If you have doubts, I'll explain again, else we'll move on.
So it's like when we are eliminating the terms, zero is like average voltage across the current through the inductance zero and average voltage across capacitor zero.
Vice
Is
versa,
it so?
average voltage across inductor is 0 and average current through
Current
capacitor is 0.
these two things we have to assume zero. Okay.
Yes, yes, yeah. So basically
Okay.
what happens is it has both DC as well as AC. So
DC.
at DC, VL is 0. So if you equate the other terms, which is dV in is equal to 1 minus d into V naught. So V naught is d by 1 minus d into V in, what you will get by doing the inductor volt
Normal
second balance. So
logic.
these two will get cancelled. Similarly, you will get IL is V naught by R into 1 minus D, which you are getting also from this model. So these will get cancelled anyways, because at DC these two are equal.
Okay.
Yes. So now I got these two expressions. So now I will represent everything in terms of state space. So IL and, sorry, this is again mistake you have not pointed out. This is dVc tilde by dt. Okay. So now I'll write the first expression something like this. So first equation 1 I am updating. Okay. So we have VL tilde. So it is DIL tilde by dt is equals to minus of 1 minus D into V naught tilde by L. Then plus V in plus V0 by L into D tilde plus D by L into V in tilde. So I have segregated everything in this way because it will be easy for me to write in terms of state space. So what I have done is I have just segregated them properly. So just cross check. If you have doubts, please stop me. Then I'll have dVc tilde by dt is equals to 1 by C, right? So 1 minus D by C into IL tilde plus, no, minus V naught by RC into, sorry, 1 by RC into V naught tilde minus 1 by RC into V naught tilde minus IL by C into D tilde. So now I have to write this in terms of state space matrix. So let's see how I am doing. So this is I tilde dot, this is VC tilde dot. So these are my two new state variables. So they are perturbed. So if you see in the actual model, you will get IL dot and VC dot because you are considering IL as whole. But now I have linearized it. I have removed the ripple. So it's a small signal model. So that's why it is IL tilde dot, not IL dot. So this is a small signal model over a DC operating point. So this IL tilde has only perturbation. It doesn't have DC value. So that's why it is called small signal model, because it is just small perturbation and also the DC value is removed. So now IL tilde, it is not related. So this is the matrix and this is IL tilde and then this is VC tilde. And one more thing I have forgotten to add, the small signal model that we have currently over here will not have any DC information. It is just only AC perturbation on top of some DC value, whereas the large signal model will have both. So IL tilde, this is 0, and then on VC or V naught tilde, both are same. So this is V naught, this is also V naught. So it is minus of 1 minus D by L. This is 1 minus D by C. This is 1 minus RC plus I have D tilde. So this is V in plus VO by L 0. Again we have V in tilde. Then this is d by L, this is 0. So sometimes what happen is people may give fixed input voltage, So input voltage is fixed. So it has only DC, then V in tilde will be 0. So then we'll not get this matrix. So you have to be clear, careful. In the assignment, I think V in tilde is 0, so you'll not get that matrix. Now if you have output, my output is V0, so it will be, sorry, V0 tilde. So this will be 0, 1 multiplied by IL tilde and V0 tilde. So I have represented everything in terms of state space. So now what we have done is we have written the equations, we have performed the state space, we have performed the averaging and then wrote in terms of matrix. Or what we can do is initially only we can write this in terms of state space and perform the averaging on the state space also. That is also okay, but this will be easier to understand since we have segregated both the equations and then combining. So that's why I have told by this method, but you are free to choose any method. But the final objective is we are representing in terms of state space. So I think some problem similar is asked in the assignment about this variable. So now you have to plug in the duty ratio as well as rest of the variables to find out these coefficients. So here I have showed for buck boost, but what will change for buck? For buck, these expressions will slightly vary, but the entire process is the same. So I suggest you to do later for buck as well as boost converter, and then do the same and then get the state space representation. And here things are simpler because it is non-ideal, and we have considered non-ideal to make you understand easy. But say if I have one parasitic, then how it will be changed? It will be slightly difficult. So you have to write the overall expression and then segregate IL, V0, and then write in terms of state space. So always start with something simpler. Here I have considered one example because it is also there in assignment, but you can also do for buck converter as well as boost converter and write and then solve. Now from here you can also get the transfer functions, so you can also calculate using inverse of a matrix. So try to solve by yourself because this, I know this week is a bit little maybe too advanced and so much content is covered. So try to solve as much as possible so that you will not make mistakes. Maybe I might have made a mistake today, but again the process is fine and I hope I have not made any mistakes. And we make mistakes if we do not practice, because I'm not doing this on a daily basis. I might make a mistakes. So how can I improve myself? I have to solve this and derive this each and every day. So I'll be in that momentum of not making mistakes and I'll be more comfortable. But since I'm not giving an exam, I'm not preparing. But if I have an exam, I would do that. I'll prepare every day so that my mistake tendency will go down and I'll be more confident with the calculations. So same thing is applicable for you. Try to derive for different converters and try to do it multiple times so that it will be easier for you. If you are learning it for the first time, it will be a bit difficult to understand and then follow. But with time, you will be more comfortable and you'll be more confident.
Sir, is there any textbook for this?
Yes,
Or
yes.
notes? You have any notes?
No. There is one good book that you can follow that is actually widely followed by all the power electronics engineers over the world. So I'm mentioning fundamentals of power electronics.
Robert Erickson. Okay.
Yes, Robert Erickson and Dragan Maximovich. And then there is another Indian version. I have forgotten the name, but it is by V. Ramanarayan.
Ramanarayan.
Yeah. So the author name is V. Ramanarayan. And then I think there is another book by L. Umanand, probably a book or NPTEL lectures also. So he's from IIC Bangalore. So just check book or lectures. I'm sure there might be book, but I'm not exactly sure, either book or lectures. Yeah. So best thing is follow the fundamentals of power electronics. They have given all the methods detailed, circuit averaging as well as state space averaging, and it should be clear. Like
Only
the book
Robert
is.
Erickson.
Yes,
So
yes.
only Robert Erickson or any authors associated with that?
Actually, it's a book written by both Robert Erickson and Dragan Maximovic. Both are the authors of the book.
Yes.
But that book itself is more than enough for power electronics engineers. So it has everything: AC to
Okay.
DC, DC to DC, all the converters, everything, soft switching, everything. But for this course, that is more than enough for understanding the power electronics basics.
Okay.
Yeah, but the trick is to solve and then practice more. Then you'll be more comfortable. Even when I have done the power electronics course for the first time, I was very scared about these tildes, V naught, IL. I'm not able to understand. But I have followed this book. I have read that book, and then slowly I understood. But only once you solve the problems, the confidence will build up. Else, the fear will always be there. So I have overcome my fear by solving more problems. As a part of coursework, the professor used to give so many assignment problems. So I was forced to solve for the marks as well as the grades. But in that process, I have gained the experience and confidence. So now I'm comfortable with these things. But at that time, I was not. So if you are also not comfortable, it's okay. That's part of learning. Only you have to overcome by solving and by practicing and learning, and eventually you'll overcome. Yes, yes.
Okay, sir.
Fundamentals of Power Electronics by Robert Erickson. So I think one student has asked. So, okay, if you have any questions, you can ask. Else, we'll end this session over here. The today's session is more about learning the concept rather than solving more number of problems. But once you learn the concept, you will be able to solve problems. Any questions?
No, sir.
Okay. Okay, then I wish you all the best. And one more announcement: I will be out of station for next session. So I think I'll postpone it because preponing is also difficult. I'll be leaving
Yes.
on Thursday. So I will postpone to either Friday or Saturday because there are only some slots that we have to select. So I will be postponing it probably Friday 7 to 8 or maybe Saturday 6 to 7. I'm just informing you ahead. And
Okay, sir.
that time it will be week 6. And week 7 again it will be normal again next Monday.
Okay, sir. Thank
This
you.
will be shared by the NPTEL. Yeah. Okay. Yeah. Thank you everyone. Thank you for
Thank you. Thank you, sir.
good night and all the best.
Thank you, sir.
Thank you, sir. Good night.
Good night.